Welcome. This video describes a data structure we call a dyad. So a dyad is a data structure that holds a left object, which could be nothing, and a right object, which could be nothing. So altogether, there are 0, 1, or 2 elements in total. If both the left and right objects are nothing, you have nothing at all. If you only have a left object and nothing on the right, you've got 1, only right, nothing on left. Also gives you 1 element. If left and right are both non-nothings, you've got 2 elements in total, maximum. And we're calling them the left and right. This is different from the pair. In the pair, there's the first and the second. In the left, in the dyad, we've got left and right. And one other difference from pair is that in the dyad, the left and right elements have to be the same data type. So we're holding 0, 1, or 2 elements, all of the same data type. Here's why you would use this. I have to say this is admittedly a little bit contrived. This is kind of a thought exercise, and it's something we want to use to compare and contrast to the pair. It's a similar but different data structure. And soon we're going to be using this to define an iterator. So this is kind of similar to a pair, but different enough that we can implement an iterator, and there will be some interesting design choices to make. It's also a way that we can practice using pointers. So it's kind of for pedagogical purposes. I suppose maybe you could use this in programming if you were trying to implement some kind of robot or character that has 2 hands. That's where the left-right concept comes from. So here's just a beautiful drawing of a person, and they've got a left hand and a right hand, these circles. And so if you wanted to program this and have an object that could be held in each hand, and it's the same kind of object, then a dyad would be a data structure that would work for that. So here's the abstract data type of a dyad, and we've listed out the operations in the same kind of notation as for other data types. So we've got a make dyad that creates a dyad that's empty, doesn't have anything to begin with. Has left takes a dyad and returns a Boolean, and that returns true. IFFD has a left element. IFF is short for if and only if. It's used in mathematics a lot. That means that has left returns true if D has a left element, and conversely, has left returns false if D does not have a left element. So it's a shorthand for writing that all out. It gets tedious to say both the true and false half with Booleans. Has right is the same thing. True if there is a right element. We can set the left to an element. We can set the right to an element. We can get the left element. Now, get left has a invariant, a requirement that has left is true. So that says get left, I give you a dyad, you give me a data type for the left element, but you're only allowed to call this if we know that has left is true, meaning there actually is a left element. So that's an example of an invariant that says you can't get the left element if there is no left element. That's nonsense. The same thing happens with get right, and there's a clear left operation that makes the left empty and a clear right operation that makes the right element empty. Finally, there's swap left and right. That takes a dyad and it exchanges the roles of left and right. So left becomes right and vice versa. Let's take a look at how we could implement this abstract data type in C++. Usually we start with the data members because all of the operations have to work with the data members. Here are my private data members. I've got a unique pointer to the left and right. The idea is that this dyad takes ownership of the left and right objects. So unique pointer is the right data type for that. Now, the default constructor is fine. I did declare it here dyad with no arguments and there's no code in there. That's okay because the default constructor of dyad will call the default constructors of all the data members, and the default constructor of unique pointer initializes the pointer to be null, meaning containing nothing. So the definition of the abstract data type is when you make a dyad, the left and right pointers have to be empty, and that's exactly how unique pointer happens to work. So the default constructor is fine in this case. And I don't write a destructor. We're using the default destructor because it will automatically free memory properly. This is the purpose of unique pointer, is that when dyad is destroyed, the destructor for dyad will call the destructor on left and right, and the destructor on unique pointer is responsible for freeing memory if necessary. So this is a benefit of RAII design. We don't have to think about that memory management, and we will not have any memory leaks in this code. And I'm setting left and setting right using the unique pointer swap operation. So what that does is if I need to set the left pointer, I'm given a unique pointer to an existing object that I want to be on the left, and I'm saying left underscore, meaning the data member, swap your contents with the passed in left. So the argument left has no underscore. The data member does have an underscore. This is always a little tricky when you're dealing with arguments that have the same names, but it's just something you kind of get used to. So what I'm doing is saying the data member swaps its contents with the passed in argument. So what that will do is the given T object for the left is now pointed to by my left pointer. So the dyad has taken ownership of this passed in argument. And then at the same moment, this passed in left pointer will now take ownership of whatever was in left underscore before. And then left with no underscore goes out of scope. So if there was an object there, it gets deleted. So again, no memory leak here. Unique pointer does all the work of managing our memory. Let's take a look at the accessors. These are pretty straightforward. I'm implementing the hasLeft and getLeft operations here. So if you look at the descriptions, hasLeft returns a Boolean, getLeft returns the left element and has a requirement that actually has to exist before you can get it. So my hasLeft operation returns a Boolean, and it just returns bool of left. And what that does is contextually converts this left underscore pointer to a Boolean. And if you check out the documentation on unique pointer, the way that works is kind of intuitive. If the pointer is null, that produces a false, and if the pointer is non-null, that produces a true. So it's a nice short one-liner there that works like we need it to. And to get the left, I assert that hasLeft is true, and then I return dereference of left. So the dereference of left says this is a pointer, dereference it, so go get the T object that's held on the left side and return it as a reference. So that's pretty straightforward, and then this assert statement is enforcing that invariant that you're only allowed to call left when there actually is a left object. So if there's not a left object and the caller makes a logic error and calls this function anyway, then we'll crash the program here rather than having some kind of undefined behavior that would be hard to debug. So here's a sketch of what these look like. Let's look at how we could develop that sketch. So a dyad has left, which is a pointer to an element but could be null, and right, which is the same thing, a pointer to an element which could be null. Now let's remember how we sketch a pointer in general. We draw an arrow, and the arrow starts at where the pointer lives. And in our case, we have two pointers living inside a dyad object. So that's why these pointers start here. This rectangle represents one dyad object. I've got the type underlined and then the left and right data members. So these pointers start at those left and right data members. And then these arrows end at the pointed to object. So that would be the left or the right elements. So up above, I have an empty dyad that has nothing. And in that case, the left pointer points at null and the right pointer points at null. So right here, that's a valid sketch of an empty dyad with nothing in it. Alternatively, let's say I have a dyad who stores in the left an int that's the value 9 and the right is an int that's value 2. So remember, these are pointers, so they're pointing to heap objects. So I would have an int that's allocated in memory represented in this square that is holding value 9 and an int in memory allocated that's holding value 2. And I have two different pointers pointing at two different objects in memory. Here's an example of how you could use this just to show off the class. So I make a dyad of int d. So this is a dyad that holds a left int and a right int. Either one could be empty. And I've print out hasLeft and then d.hasLeft. So this is just showing off how the hasLeft and hasRight functions work. And then I set the left to 5 and the right to 9 to correspond to that sketch. Do the hasLeft hasRight thing again to see that it changes. Print out the left and right contents. Then I do this swap left right operation, and we print out the left and the right. So if we look over here, hasLeft 0, hasRight 0, those are false Booleans to begin with because the default constructor makes this empty. Then I assign them, and now they're true, 1. All of this is working here, set left, set right, and left and right accessors because it prints out 5 and 9, and then swap works because it prints out 9 and then 5. Okay, so that's dyad. We'll be working with this some more later on.